This material has been excerpted from the college television course, The Mechanical Universe, and re-edited specifically for use in the high school curriculum. The Mechanical Universe is funded by the Annenberg CPB project, made possible by a grant from the National Science Foundation.
In his own time, Benjamin Franklin was known to his countrymen as the wisest and the most worldly man the young colonies could offer. In England and France, he was a legendary and wildly popular figure. Today, we think of him as a statesman who dabbled in science. He was, in fact, a serious and very important player in the history of science. And by far, his most important scientific work had to do with electricity. In the late 18th century, people around the world were fascinated by the phenomenon of electricity. In Europe, experimenters had produced large electrostatic machines and arrays of Leyden jars. The Leyden jar was a device used to store electrical charge. But beyond the laboratories, particularly when it came to the famous Philadelphia, the business of electricity could be positively perilous. In fact, when Franklin tried to cook a turkey by electrocution, he almost managed to electrocute himself. In his own words, Franklin described the dangers of electricity. It seemed a universal blow throughout the body, followed by a violent, quick trembling in the trunk, a swelling raised on my hand. My arms and back of my neck felt somewhat numb. My breastbone was sore for a week. Obviously, Franklin had discovered how not to conduct electrical experiments. For the record, however, this error was as rare as the man himself. After all, he was the first to publish a theory of electric charge and electric force. The details would be worked out later, but in modern terms, where was Franklin headed? In the vicinity of a positive charge, the electric force, indicated here by a red arrow, repels a positive test charge. An external force is needed to push the charge closer, doing work against the electric force. Positive work if the motion has a component opposite to the electric force. Negative work if it has a component along the force. And no work at all if the motion is perpendicular to the electric force. Work is equal to the change in the electric potential energy of the test charge. This work can also be found by multiplying the test charge by a certain quantity. This quantity is called potential difference. Thus, potential difference can be defined as work per unit charge or change in electric potential energy per unit charge. Potential difference is measured in volts. 100 years before Faraday discovered the electric field, Franklin saw it as the electric atmosphere. In his theory, the atmosphere arose from a fluid, an electric fluid that permeates every object on Earth. Everything in turn was a sponge of sorts, which might soak up the electric fluid. Franklin said that when an object soaks up too much fluid, it's positively charged with electric fluid. But if an object doesn't have enough electric fluid, then it's negatively charged. He said that positively charged objects and negatively charged objects attract each other. But two objects that are both positively charged repel each other. Franklin's terms, positive charge and negative charge, are still in use. But with better understanding, their meanings have changed. Today, it's understood that there are, in fact, two different types of electricity, positive charge and negative charge, and that all objects in nature contain both types. Nevertheless, Franklin had realized correctly that electric charge is something that's never created nor destroyed, but merely flows from one object to another. Today, what Franklin saw as the electric atmosphere is seen in modern terms as the electric field. An electric field is present around any object that carries a net electric charge. Of course, if an object's positive charge and negative charge are balanced, the object is electrically neutral, and it produces virtually no electric field far away. But even beyond that, the static electric field inside any piece of metal is zero, which means a test charge would feel no force at all inside the piece of metal. And that's true even if the metal has a net electric charge. That's because the charge piles up on the surface until there's no field left inside to make it move. Of course, electrically charged conductors do create electric fields outside themselves. But inside, there's no field at all. And because there's an electric field between two oppositely charged pieces of metal, there's bound to be a difference in potential between them. But since there's no field inside, the potential is the same everywhere in the metal. So, each piece of metal is a region of constant potential. The potential difference between two pieces of metal depends on how much net charge each one has. Negative charge lowers the potential, as shown on the graph of potential as a function of distance from the charge. And positive charge raises the potential. Of course, in the 1700s, Dr. Franklin was in no position to get such a clear picture of electric potential, for even its concept was unknown in his day. But he did have an enormous knowledge of electricity, which he often shared with his colleagues throughout Europe. And as the wisest American, Ben Franklin also paid considerable attention to the great minds of the past, particularly Sir Isaac Newton. Franklin was well aware of Newton's theory of universal gravitation, and he knew the force of Newton's gravity unites the universe by causing masses to attract each other. Franklin would have liked to formulate a similar law, a law of electric force. But it doesn't quite work, because unlike gravity, there are two kinds of electric charge. Electrical charges that are unlike attract each other, and charges that are alike repel each other. That's one reason why an ordinary battery has the potential to create an electric field. When a battery is connected between two pieces of metal, it forces charge to flow from one to the other until the potential difference between them is equal to the voltage of the battery. That creates an electric field between them. If the voltage is doubled, so is the charge. So is the potential difference. And so is the electric field. In general, the charge transferred is proportional to the voltage applied, and the constant of proportionality, C, is called the capacitance. Long before there was a modern capacitor, much less the means and mathematics to illustrate how one works, everyone in the world knew about lightning. But to discover the role of lightning in the world of natural science, one had to follow Ben Franklin into the study of electricity itself. Of all the 18th century electricians, only Franklin had seen lightning bolts for what they are, huge sparks of electricity, no different from the kind he could create in his laboratory. On paper, there was the basis of his theory. First, extend a metal pole, the lightning rod, from the roof of a building. Then, place a wire near the rod. In theory, the rod would draw some electricity from the stormy sky, and a spark would jump from the metal to the wire. Instead of using a lightning rod to draw electricity from the sky, he used a kite, a simple apparatus made of twigs and a silk handkerchief. And instead of a separate wire, he attached a metal key to the kite string. On the fateful night, he noticed loose threads standing out from the kite string. Then, just as he had bravely predicted, the sparks jumped. And as they zipped from the key directly to his bare knuckle, Franklin experienced a feeling he'd never forget. But in fact, Franklin's greatest discovery was not made with lightning bolts. It was made with Leyden jars. And it was here, rather than in the stormy sky, that Ben Franklin revolutionized the science of physics. Others assumed that when they charged a jar with electricity, they were adding large amounts of electricity to it. But Franklin knew better. And with his knowledge, he was the first to figure out how a capacitor worked. He realized that the electric fluid was neither being created nor destroyed. It was merely flowing from one place to another. In a Leyden jar, it was flowing from the conductor inside the jar to the conductor on the outside. In other words, the Leyden jar was the first primitive electric capacitor. Any two pieces of metal can form a capacitor. The shape doesn't matter. The two pieces of metal can be the plates of a parallel plate capacitor, or they can be the inner and outer parts of a Leyden jar. The electric field in a parallel plate capacitor is really due to sheets of opposite charge facing each other on the metal surfaces. The field between the sheets is constant. The two sheets of opposite charge attract each other and hold each other in place. That's why a capacitor is such a useful device. If the voltage is held constant by a battery, the charge, and therefore the capacitance, changes inversely as the distance between the plates and is proportional to the area of the plates. Franklin realized that if capacitors were connected together properly, they would create a larger capacitance. Properly meant in parallel. A series of Leyden jars, one after the other, actually created a smaller capacitance. But a parallel bank of Leyden jars proved to be an excellent arrangement, and Franklin called it the electric battery, another term that has a different meaning today. But the important thing is not the term, it's the idea. And only Ben Franklin realized that it didn't take a fancy Leyden jar to hold on to electricity. A simple pair of parallel metal plates would do. Despite its occasional inaccuracies, Franklin's work with electricity was a scientific milestone. But even so, Ben Franklin will always be best remembered as a statesman and a remarkable public servant. Here in Philadelphia, he established the first public hospital, the first public library, and the first fire department. As a delegate to the Albany Congress of 1754, he had been so bold as to propose a union of the colonies. In this room, with the diligence of a scholar and the moderation of a statesman, he set the course and molded the ideals for a newborn nation. But as a scientist, Ben Franklin was the greatest of the natural philosophers. Not only then, but today, throughout the world of science.
This material is based upon work supported by the National Science Foundation under grant number SPE 8318420. Any opinions, findings, and conclusions or recommendations expressed in this program are those of the authors and do not necessarily reflect the views of the National Science Foundation.